All right. Hi, everybody. So today I'm going to be talking about predicting products for single replacement reactions. And something that we are going to be focusing on is the reactivity, also known as the activity series. So you'll need to reference this thing, which is on the back of your periodic table. So basically, what it is we have this reactivity series, which looks at metal cations. And that's what this is right here. So if you notice, every single one of these, except for this one hydrogen right here, these are all metals, all metal cations. And not every single replacement reaction will occur. We have learned so far that you can just kind of predict, like if we were looking at this, like is going to replace like, and then, so in this case, the strontium would switch with the iron, strontium and chlorine would end up together, and iron would end up by itself. That could be the case, but that might not be the case. So what we're going to do is we're going to look at single replacement reactions and look at who will actually switch with who. Sometimes there will be a reaction and sometimes there will not. So what we need to do is we need to identify the two cations in a reaction to figure out whether it's actually going to take place. So if I look at this example right here, I have strontium and I have iron. And what I'm going to do is I'm going to look at this diagram right here, and I'm going to locate strontium and I'm going to look at iron. Strontium is higher up in the series. It's on the most reactive side of the spectrum. So here's strontium and here's iron. Iron's in the middle. So who's more reactive? Strontium is more reactive than iron. So what I'm going to do is I'm going to write high right here so that I know strontium is more reactive, and I'm going to write low right here so that I know that iron is less reactive. Typically what will happen is the more reactive element will kick out the less reactant element. So in this case, strontium is by itself, iron is less reactive, so strontium is going to kick out the iron in this reaction. So that means strontium and chlorine will end up together and iron will end up by itself. So I will end up with SrCl2 plus Fe. That's the reaction I'm going to get. So what is happening? So right now, this iron is an ion. It is in an ionic compound, so it is an ion. This strontium right here is a neutral metal. It's got the same number of protons and electrons. So what will happen is this strontium right here is going to donate its valence electrons to the iron because it will lose electrons, hence why it's a cation, right? And it'll end up in this compound because it donated its electrons to the iron. So iron right now has less electrons, but what strontium will do is it will kick out the iron, donate its electrons to iron so that iron can go be all by itself, all by its lonesome. Let's take a look at the next one. So we're looking at barium and we're looking at lithium. So if we look at our reactivity series, barium is right here, lithium is all the way at the tippy top. So lithium is high, barium is low. So lithium already is more reactive. So do you think that lithium is going to be able to kick, or that barium is going to be able to kick lithium out of the compound? No, because lithium is already more reactive. So if lithium is already more reactive, barium is less reactive. Barium cannot kick lithium out of its compound. So this will be no reaction. There's no reaction that can take place. Lithium is higher, barium is lower. It's not going to happen. In this next example, we have copper and we have silver. So if we take our reactivity series, here is copper and here is silver, all more towards the bottom. So who's higher? Copper is higher, silver is lower. So copper is high, silver is low. So in this case, can this reaction occur? Yes, this reaction can occur because copper is higher. It's more reactive. So copper is, like I like to say sometimes, copper is top dog. Copper has the ability to kick silver out of its compound. So if this does happen, copper will kick silver out. So we will have copper nitrate and silver is going to end up all by itself. The higher top dog, right, because it's towards the top dog kicks out low dog, it will take its place. Now, I know we don't know what copper charge this is right here, so I'm just going to pretend that it's +1, so that's why I put them together. Most of the time, you'll be told what charge that is so that you can figure out what compound to make. Let's take a look at this next one. Now we have copper and we have hydrogen. Now, I know hydrogen is not a metal, but in many cases, hydrogen is a cation. And in this series, we have hydrogen right here and we have copper right here. So hydrogen is higher. So hydrogen is high, copper is low. So right now, the top dog, the hydrogen, is in the compound. Do you think the low dog can kick out the high dog? No. So this reaction is not going to occur. There's going to be no reaction because hydrogen is already higher than the copper. So that's how you figure out like what's happening with metals and metals only. Now, there is another reactivity series on our periodic table that is not in some sort of reference box anywhere. So what I want you to do right now is I want you to pause the video, and I want you to take a look at these reactivity series, right? If you look from here to here, this is representing the halogens. This is your only metal. Potassium is your only metal. Non-metal, 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 non-metal. So same thing. Potassium is the only metal in this entire set of reactions. So what we're doing is we're focusing on the halogens. So if you look here, this reaction occurs, this reaction occurs, this reaction does not occur, and this reaction does occur. So pause this video and take a moment to see if you can figure out why that is. Okay, so if you think you've figured out what's going on, let's take a look at the things that are switching. Chlorine is by itself, and potassium starts with iodine. Then over here, potassium ends up with chlorine, and iodine is by itself. So what's switching? The chlorine, the iodine, the chlorine, the iodine. Same thing here. It's the halogens that are switching. Here are halogens. Nothing happens. So if you were having a hard time trying to figure this out, we need to reference our periodic table. So if we look at our periodic table and we look at the halogens, look at them. They're all right here. Fluorine, chlorine, bromine, iodine. If I look at this reaction right here, here's chlorine, here's iodine. What is their relationship? Chlorine is up here, iodine is down here. Chlorine's higher. Reaction occurred. Look at this one. Chlorine's here, bromine's here. This reaction occurred. Here's chlorine, here's bromine. Chlorine, again, is higher. I look at the next reaction. Chlorine, fluorine. Fluorine, chlorine. Oh, fluorine's higher. No reaction. And then what happens here? Fluorine, chlorine. Fluorine's by itself. Chlorine is in a compound. We already just said fluorine's higher, so fluorine takes over. So what's the trend? Well, if you have a halogen that is higher up in its group, fluorine up here, iodine up here, the higher up in the group it is, the more reactive it's going to be. Just like we saw on our reactivity series, the higher up it is, the more reactive. The lower, the less reactive. So the pattern is the higher the halogen in the group, the more reactive. Okay, so in this case, fluorine was top dog, kicked out chlorine. In this case, chlorine was not top dog. Fluorine was top dog. So chlorine cannot kick out, low dog cannot kick out high dog. And then in this case, chlorine's higher than iodine, it can kick out iodine. Chlorine is higher than bromine, it can kick out bromine. All right, so that is how we figure out the activity series for metals using that chart on the back of your periodic table, or for halogens using the group 7 ranking. All right.